welcome to our short lesson on Kepler's laws. We're going to look through a few characteristics about our solar system that's going to help us determine how we're going to use this law. And we basically use this law whenever we want to find either the distance between the sun and a planet or the period of revolution between that planet and the sun. So here's the first thing we're going to look at. Planets move in elliptical orbits with the sun at one focus. So let's just say we have the sun here. This is our focal point, and our planets revolve around the sun in an elliptical orbit fashion. So let's just say we have a planet here, and it's going to move around our sun, not in a circle, but in an elliptical fashion like that. And also, the distance between the sun and a planet is the radius of the orbit. And this is other radii to describe our elliptical orbit. And the area between each of these are going to be the same as indicated in the second part of the law. So it states the straight line joining the sun and the planet sweeps out equal area in equal time. So again, here's a diagram. This is our sun. And let's just say that this is our Earth. This is a radius, or the distance between the Earth and the sun at a given time. And then let's just say 1 month passes and our Earth is located here. I'm going to call this area between 1 month of the Earth's movement as area number 1. And let's just say our Earth continues to move 1 month later, and our Earth is now located here. I'm going to call the area between this next month as area 2. So Kepler's law states that area 1 and area 2 are equal to each other. And also the time duration is equal to each other. And we indicate that as the first month and another month after that. So the time period between those two times are the same. Okay, the third part of the law states the cube of the distance from the sun is proportional to the square of the period of revolution. So our distance from the sun, we're going to say that's r for radius. And it says the cube of that distance is proportional to the square of the period of revolution. I'm going to say that's t for period of revolution, because that's a time period that it would take a planet to go around the sun. This is called K for Kepler's constant. We're going to use this result a lot to help us determine the distance between a planet and the sun, or to determine the period of revolution for that specific planet. Before I begin and do an example of this, I'm going to make a side note that when we describe the distance between the Earth and the sun, it's actually easier to describe it in astronomical units instead of meters. Just because the distance between the Earth and the sun is 1.49 times 10 to the power of 11 meters, that is a lot to write and to say, so we could just write that as 1 astronomical unit instead. So here's your side note. Earth's distance to the sun is 1.49 times 10 to the power of 11 meters, which is also equal to 1 astronomical unit. And sometimes you would see this unit for other distances between other planets and the sun, and it'll just be a different number. But for our sake, between the Earth and the sun, that's 1 astronomical unit. Okay, so now let's go ahead and do an example. So the Earth is 1.49 times 10 to the power of 11 meters, or in other words, 1 astronomical unit from the sun. We also know that the period of revolution for Neptune is 60,185 days. We want to know what is the distance between Neptune and Sun. In other words, you can say that what is the orbital radius? That's another way of saying it. So just be familiar with the different terms that we could use in these type of questions. Okay, so we're going to use the result from number 3 to help us with this, which is the distance cubed divided by the revolution squared. And we're going to relate this between the Earth and Neptune. So my little e here is for the Earth, and my n represents a Neptune. So for the information we have everything except for our n, and that's what we're looking for. So I'm going to rearrange this as r cubed subscript n. So the distance between Neptune and the Sun will be equal to the time period of Neptune squared multiplied distance between the Earth and the Sun cubed, and then our time period of our Earth squared. And all I did was multiply both sides by Tn squared to get this. Okay, now we're going to fill in the information that we do know and solve. So our period of revolution for Neptune is 60,185. We're going to square this. We know that the radius, the orbital radius of the Earth is 1.49 times 10 to the power of 11 meters, and we're going to cube it. And then for our time period to orbit around the Sun for the Earth, we are going to express this in days. As you can see, we have it in the question here that the period of revolution is in days. Well, approximately, we always say is 365 days to go around the Sun, and that's how many days are in a year, but to be more exact, it's actually 365.25. And that's why we always have those time changes and our leap year to count for that, 0.25. So just a reminder here that TE is 365.25 days. Alrighty, and now we're going to go ahead and put this into a calculator and solve. So the orbital radius of Neptune cubed is 8.98 times 10 to the power 37 meters. And then we're going to cube root this to solve for Rn, which is 4.5 times 10 to the power 12 meters. And that is our final answer. You don't have to change it into astronomical units if you don't want to, but just take a note that there are going to be questions that are given in astronomical units, and you should know how to convert it to meters if need be.